Now, hello YouTube, welcome back to our discussion on the filtered Navier-Stokes equations. So, the last video we were trying to say that, okay, I want to make the filtered Navier-Stokes equation, something like this, look something like this, okay? So, this will look exactly like the laminar Navier-Stokes equation, except for a few extra terms here. So, how do we get these extra terms? How do we get to here? How do we get okay, let's see. How do we get from here to here? All right. And remember, this is an Einstein notation. I have, for every j, I have one in each x, y, and z direction. So this is a uj. It will be representing three equations here. And I have this xi over here. When you have the notation I, it is representing the what do you call that? Summation. Summation in the x, y, and z direction, so that you have your divergence terms over here. Okay. Where is your divergence? This is the divergence term here. Remember, I expanded it out. I explained it in the last video what these were. Okay, and how do we get from this equation to something like this? All right, and firstly, we need to get from here to here first. We need to get the difference between these two, and this is where the extra terms will come about. Okay, so when we do this, we can just say we have some residuals. Okay, so the difference, okay, this isn't the right one. Should use this. Yeah. This is weird. Okay, never mind. Yeah, so what is the difference? So what is the difference between this and this? Okay, so the difference is measured in, like, Reynolds stress. Okay, so this is a subgrid scale. This is a subgrid scale, or residual Reynolds stress. So you remember, in your Reynolds average Navier-Stokes, there are some extra terms that actually hung around after the whole averaging process. These were these terms in the Reynolds average Navier-Stokes. In a similar analogy, we can just lump every term that is different between this and this under a Reynolds stress. These are stresses due to the small turbulence that we have to model, and we don't resolve directly through the simulation, but we model much like we do a k-epsilon, in a similar concept of k-epsilon, but it's not exactly the same. We just model these small subgrid scale, meaning to say smaller than this delta that you specified. Okay, so delta is the characteristic length which we of the filter, where we say, okay, for all those funny eddies that are smaller than this delta, I don't want to care so much about it. So that's roughly what delta means. So how do we model all the effect of these smaller eddies? We basically model them as an increase in the viscosity. Increase in viscosity of some sort for a viscosity model or some other kind of model. So we lump this thing together under Reynolds stress. Alright, so we can just write uj equals to this term plus tau ij r. So these are the additional Reynolds stress terms that are in the subgrid, okay, which are smaller than your delta. This is the effect on the filtered velocity. Other than that, we don't really care. Excuse me there. Yeah, so we model it as some sort of Reynolds stress, and then we use some kind of empirical model, fudge model, to try and get this done, to resolve this. So if we just apply the differential operator, del by del xi, we just apply this differential operator, partial by partial xi across the board. So I will result in these two terms. Okay, and then earlier we already found out that this we can simplify from the continuity equation. We can get rid of this term and we'll just be left with this. So we will have this whole term here simplified into this term. So I'll just copy and paste this here, and I will paste this back into our equation here. Okay, I'll substitute these two terms back here, and I'll just bring this over to the other side. Okay, minus, all right, I'll bring that over to the other side and we are more or less done. Okay, so this sort of looks like a substantial derivative, so we can actually define the substantial derivative, except we can use a bar instead by d bar t. Okay, so this is what we are having here. So this is equals to partial by partial t plus u, I think it's I bar, okay, ui bar into partial by partial xi. And that's how we get the equation there. So we can of course write it in this form. And we will get the equation that is more or less represented here. Okay, so these are the terms that contain all the prime, whatever the difference is. Okay, yeah, they will contain all of these funny little terms, and they will account for that difference. Okay, so these are in the residual terms, in the Reynolds stress terms, which are caused by the subgrid scale turbulence. Okay, so subgrid scale turbulence is like so. Good. Okay, so all right, now that we have this equation, the question is, the trick is, how do we find this extra little stress term? Okay, this Reynolds stress term. So that is that will differ from LES model to LES model. This differs for each LES model. Okay, so this is more of an art than a science, so to speak. Is a way of, you can either use empirical fits or use some constants and all. And the most common way is to model it as the easiest way is to model this extra shear stress. This is step 3, of course, of doing LES. before we run our simulation, we model our shear stresses as extra viscosity. So we'll have this kind of thing going on here. Okay, so shear stresses are made in this fashion. Okay. So now you can actually model this as some sort of a extra viscosity here. Okay. We can model this as a turbulent viscosity or momentum diffusivity in subgrid scale. So remember, when we use this term called subgrid scale, I mean, you'll see it a lot in literature. Subgrid scale means anything that's smaller than that delta, characteristic length scale of delta, which you picked. Or it will differ from model to model, of course. Okay. Alright, so subgrid scale. So we can turn this into something pretty simple. So this is just tau equals to nu okay, this is yeah, there will be stresses here, which okay, anyway, so yes, how do we model that? Okay, let me cancel this first. Yes, let's model this tau as some viscosity into some rate of strain, which is this velocity gradient over here. This is pretty simple. Remember, in Newtonian viscosity, we have tau equals to mu u partial y, for example. I didn't specify the direction, but this is what the equation would look like. So in more complicated coordinate system, you'll have this kind of thing happen. So where Sij will be this these two velocity gradients. So these two will cancel out. Okay, and then you'll have just the turbulent viscosity multiplied by this filtered rate of strain. Okay, this is the Sij over here. All right, and then you want to substitute this into the partial by partial x. Okay, and then you will just get this. Okay, and that's how we do it. And then we substitute back in here. Substituting back in here, and we will get a positive term here. All right. So in total, what happens? You will have this thing happening. Okay, so you'll have more or less this sort of equation happening. You may see it being used in different assumptions. I mean, different assumptions will result in different forms. Of course, we can cancel this term out depending on the assumptions we use, but generally we just leave it there first. Okay, so what we have is that we have this extra little turbulent viscosity or eddy diffusivity. Okay, so that's the long and short of it. Okay, so the rest can be solved by Navier-Stokes. The question is, how then do we get turbulent viscosity? Okay, so yeah, this should all be part of step 3. Okay, this should be part of step 3. Yes. So we substituted in, and then we substituted all this into the Navier-Stokes equation to get a filtered Navier-Stokes equation. Then we try and model this residual shear stress. Usually, the simplest way is to get the viscosity. There are more complicated ways of doing it, but I'm just introducing the simple ones. Okay. So this extra viscosity we add is very similar to the Reynolds average Navier-Stokes, but derivation is different because the filtering process is not the same as the time averaging process. Just a reminder for you, all of these are pretty different. So how then do we get nu T? So let me just introduce to you the Smagorinsky model. Okay, it's used by this guy called Smagorinsky from 1963, if I'm not wrong. Okay, he used it for LES modeling of atmospheric turbulence. Okay, so this is a very simple model which says this. Okay, so Smagorinsky model is one of the classes of turbulent viscosity models for subgrid scale turbulence. Subgrid scale meaning smaller than your delta. Okay, smaller than delta. So we have a subgrid scale turbulent viscosity model. So for Smagorinsky, he gives this term. Gives this what do you call that? This formulation. So viscosity is generally in terms of meters square per second. Okay, this is a momentum diffusivity. So this is the units of kinematic viscosity are length squared over some time. So how he modeled it is use a characteristic length squared times 1 over time. Okay, where do we get this 1 over time? Okay, so I'd like to introduce to you this thing called the characteristic filtered rate of stream. So this is what it is here. So S bar equals to 2 into square root of 2 into Sij bar. Sij bar into Sij bar. Remember Sij bar is this term here. Okay, recall. Sij bar is this. You just substitute this into the square root term here. You will just get the following. Okay. All right. So if we were to just cancel this terms out, we will get something like this. It's sort of a root mean square kind of a formula. But what I want you to note is the units of this. Okay, this is more important is the units. The units on top are meters per second, and the bottom is also second. So this is meters per second squared. Okay, oh, not meters per second squared. The bottom is meters. So these are actually in units of 1 over time. Okay, and this gives a pretty good estimate as to some relevant time scale. So this S bar is actually in units of 1 over time. Okay, this is 1 over time, and that is where Smagorinsky got his 1 over time. All right. So we put this S bar over here. And what is the characteristic length scale for this turbulent viscosity in the subgrid scale? So what he did was just this. L characteristic the length scale, characteristic length scale equals delta, because delta is definitely a length scale that we are interested in. And then he just puts a constant, the Smagorinsky, one of these Smagorinsky constants. In other words, also known as the Smagorinsky coefficient. So when we substitute this back into the viscosity here, we will just get this. Yeah, we will have this C smargorinsky into delta squared times S. So this is what this Smagorinsky model does for you. Okay. Okay. So this is a Smagorinsky constant. There are some ways of deriving this, or you can do some experiments. So C, depending on where you find, you can set it for your equation. It can be 0.17, 0.15, okay, 0.17 for some, 0.15, 0.2, 0.25. So that means it can range from 0.15 to 0.25 depending on your simulation. Of course, this is just empirical fit. You have to fit it to your equation, to your experimental data to find the best value for your simulation. Okay, so this is the nice thing about Smagorinsky model is that you only need to define one parameter, which is this coefficient. But of course, the trick is then, the question is then how to specify C and specify this Smagorinsky coefficient. All right. I hope I'm pronouncing his name right. Yeah. So the question is, how do you specify this C Smagorinsky? Because generally, when you try to hop from one case to another, this Smagorinsky coefficient, the best Smagorinsky coefficient will kind of change. So you kind of have to look at literature online, to kind of see, and you do experimental search, experimental data, or well, maybe the other way is to use some other more complicated model. Okay, so this is just one of the most basic models for large eddy simulation. This is a Smagorinsky model. You can see it's very rather simple to implement. We just need to define what is this delta and what is this Smagorinsky coefficient, and then basically the equations can be solved. All right, as long as your grid is small enough, that you can resolve these eddies, then this should not be a problem. Okay. However, of course, the computational power with that is very high still. Some laptops may not be able to take that kind of thing. And it will still take a while for most computers. But this is the gist of large eddy simulation. Okay, for the most simple versions. So I'll stop for the time being. I'll see you guys next time where we can talk about other pertinent issues with this model. If I have the time, yes. Okay, bye bye.